All right, we have here a kind of novel example. I'm actually going to show part of the answer in pictures and then work out the rest on the whiteboard. So I'm also going to be doing this a little bit different than I usually would do, I guess. Anyways, the situation is we have an ogre that rides the Loop, which I guess is an interesting name of a ride. I have to say I actually stole that from a physics textbook, that name. And he notices that he feels exactly weightless at the top and quite a bit heavier at the bottom. Assuming that the ride moves at constant speed in a circle with a radius r, how fast would it need to go for the ogre to be weightless at the top, and how much heavier than normal is the ogre at the bottom? So those are two interesting questions. And to start this off, like I said, I'm going to look at the answer because it points out, well, his velocity is tangential at both places here. He's in uniform circular motion, right? The acceleration naturally is in a centripetal direction. So for both the top and the bottom part, they are now drawn in the picture and both pointing towards the center, but oppositely directed, therefore. So we can do an FBD at the bottom, right? And there's going to be gravity, and there's going to be a normal force. There they are. And notice that at the bottom, the normal force is quite a bit bigger, and that might explain why the ogre feels a lot heavier. Is it really that gravity pulled stronger, or is it just that the cart is pushing up on the ogre with a larger force? We're going to look at a different FBD at the top. Gravity is still going to point down. The normal force is small or non-existent. So when I say that it could be non-existent, why would that make sense? Well, if he says that he feels exactly weightless at the top, it turns out that feeling would come from momentarily the normal force that normally would be supporting the ogre in his seat disappearing, and thus he feels briefly weightless. It turns out it's not really a change in gravity. It's just kind of like a change in circumstance, really. Both these diagrams, though, you can kind of relate them to the acceleration that's involved. For this one, why does a normal force need to be bigger? Well, it needs to counteract gravity, and there needs to be a net force up to explain this acceleration. And again, it also explains the experience of the ogre. Whereas at the top, gravity is actually all that's really needed. If the speed is maybe just right, then the normal force can disappear, explaining the weightlessness, and gravity is just right to supply the needed acceleration. So let's actually analyze. Let's do an F equals ma on that top situation, and maybe I'll say I'm gonna call this the weightless F equals ma, because we're looking at that scenario with that free body diagram, and even though there's a little tiny normal force drawn in there, I'm going to assume that it's not even there. And so I'm just going to say, hey, there's gravity force is equal to mass times acceleration, and I'm just going to keep things simple and say that maybe this is a lot of steps all at once, but everything's kind of one-dimensional here. I'm not even worrying about coordinate systems so much. Gravity pulls down, acceleration is down. If I'd been really picky, I could have made these minus. Instead, I'm doing the y component, but you know what? Don't need it. The mass of the ogre cancels out here, and in that sense, when it said here, how fast would it need to go for the ogre to be weightless at the top, I think a solution presents itself, because I can solve for v squared by multiplying both sides by r, but then that implies that v is equal to the square root of g times r. And this being a problem that did not really give us any numbers, but was kind of like stated in a very formal fashion, this is the best answer I can give for that. But now it asks us, how much heavier than normal is the ogre at the bottom? And keep in mind, the ogre's normal weight is going to be mg. So, maybe I'm going to now do an analysis of the heavy portion of this. That's really the bottom. I guess I could have called it bottom, but I'm trying to parallel. I call this weightless, and then we're talking about the heavy part of the ride where the ogre feels heavy. We're going to do an F equals ma for that now. And for that one, definitely the normal force is going to have to be part of that. So I'm going to throw that into my forces here. It's in the diagram, very large. So there it is. The normal force, I'm going to consider that the positive direction. So we're going to look at normal force. Actually, let me make this a minus. Gravity points down, right? So we're going to make the Fg force turn into a minus mg. Again, following the picture there, right? So this one's plus, this one's minus. Acceleration is up for this heavy part, and it's up by an amount that's equal to v squared over r. So how do we deal with this situation? Well, something to recognize here is, since v is said to be constant for this situation, it says assuming that the ride moves at constant speed. So this v is the same as this one, and really this equation before I canceled the masses had said that mg, representing the weight of the ogre, is equal to mv squared over r. So really this is just equal to mg. And if I add mg to both sides, I get normal force is equal to twice mg, right? Because I'm going to add it to cancel here, but then mg plus mg would be 2mg, which implies for that second question, how much heavier than normal is the ogre at the bottom, is, I'm just going to say it's twice as heavy, because he feels a normal force equal to twice his normal weight. And so I think the last slide toggle out I'm going to do here shows those two answers, v equals square root of g over r, and his weight, in quotes, is double at the bottom, which is in alignment with what I said.